Hi everybody, it's Mrs. Dinkelman, and this is the notes for 4.3 where we're talking about absolute extrema and the mean value theorem. So kind of two parts to this video. I will mention where I think you should pause and get going on the assignment for the first part, and then maybe you can come back and do the rest of the assignment. So at the beginning here, there's kind of some informal definitions about what we're going to talk about in calculus as far as maxima and minima. So you're going to see, excuse me, absolute maximum, absolute minimum. So like the absolute greatest y coordinate that we can find, or, smallest y coordinate we can find. And then the ones that we tend to do a lot more in calculus are the relative or local maxima and minimum. And those are kind of the hills and valleys that you probably looked for when you did polynomials and that kind of stuff in pre-calculus. If we say extrema, or they ask you to find the extrema, they're talking about the mins and the maxes. And then finally, critical numbers. There is where the derivative is either 0 or undefined. We're going to use those critical numbers to find our maximum and minimum values. So first here, there's a theorem, the extreme value theorem. So we have a continuous function f on a closed interval. So we have to know that a and b exist at the end of this. That it has both a minimum and a maximum. And I just like to always mention in this particular case that even the function that's just a horizontal line has a minimum and a maximum. It happens to be the same thing, but that is a continuous function, so it does have to fit this extreme value theorem. And if you look at the definition again for the absolute max and absolute min, it says it's greater than or equal to, and that's why for a horizontal line we end up having an absolute max and an absolute min. Okay, so for this particular assignment, they're going to be asking us to find the max and min on a closed interval. So this is kind of the steps for finding the absolute max and the absolute min. We're going to find all the critical numbers. So again, remember back from just a moment ago, we talked about critical numbers being where the derivative is 0 or undefined. And then we're going to have to find the y values at each of those critical numbers and also the endpoints. And we'll kind of look at some pictures about why we have to check both. Out of that, we just choose the least and the greatest y values for our absolute max and then our absolute min. Okay, so a couple notes here. Again, the absolute extrema, they can either occur at the critical numbers or endpoints. This is why we have to check both. And then it says we will not consider endpoint extrema to be relative, although some textbooks allow. So we'll talk about just local mins and maxes being at the hills and valleys, but not at the endpoints. But again, some textbooks do. And AP exam graders and people know that, so they tend to not ask us that question just in case. Okay, so looking at the figure on the right there, absolute maximum, normally what we're looking here is for the y value, and then later they'll ask us at what x value does that occur. Absolute minimum. So here's the really interesting thing. No, sorry, I was thinking it was asking for the point there, but this is going to be at -4, 4. Absolute minimum. So here's the issue with this one. It's not continuous on the closed interval. So we can't actually name the absolute minimum because we kind of know where it is. We could kind of describe it. It's like the point that's just greater than -2, but we can't really name that. Like we can't write down the decimal for that. Just a quick side conversation. We could not say -1.9 repeated. That is not less than -2, or greater than, I should say. And we can have this conversation maybe in class. It turns out that -1.9 repeated is equal to -2. Whole different kind of conversation. So that doesn't work. We just can't name that point, so we can't say that we have an absolute minimum. Relative minimum. So again, relative minimums are going to be, at least here, it's going to be the valleys, I like to call them. So it says at what x values. So let's say that's at x is -3, and then there's another one when x is 1. And then maximum, so we're looking for the hills. Oops, we can't really do that one because it's a point that doesn't exist. So we're just going to say at x equals -1. So back to global extrema or absolute extrema, and that's what we're tending to look for in this section, is I always like to start a list. I'm going to have to check the endpoint, so I'm going to figure out what f of -1 is here in just a second, and f of 3. And then I'm going to figure out what the derivative is here and find our critical numbers or critical values. So that derivative, drop the 3 down, that's going to become an x squared minus 4x. Luckily, this one is never undefined, but it is 0 in a couple of locations. So x is 0 and 4. Well, 4 is not in our interval, so the other thing we're going to check is just the 0. So here's why we're checking endpoints and anywhere the derivative is 0. So it could be that our endpoint is the max. Okay, so we want to check the endpoint. It could be, though, that the spot where the derivative is 0, the little hill there, is the absolute maximum. So we're checking both just in case because we're trying not to have to look at the picture here. So I did a little bit of work earlier, and maybe you can double check me. I plugged -1 just into this original function, and I got -2 1/3. And then I plugged 3 in, and I got -9. And then I plugged 0 in and got 0. So now we can just kind of look at those y coordinates and say the absolute max, I don't know how to spell absolute max, or global max if you want to use that, is actually 0. And then the absolute min would be -9. And we just need to see here, you know, I feel like this question isn't super particular, but does it want to know where? Does it want to know what the max and min are? So I'm just going to go with that's what those are. 8, find the absolute max and min values of x minus 2 in the interval. So for me, I would rather not take the derivative of the absolute value. I would rather just draw the picture here. So I know this is a v that's moved over 2, and we're going 0 to 5. And so I can just look at the graph and find the absolute minimum. And that's at 0, and it occurs at x equals 2. Okay. And then the absolute max, so let's think about what that's going to be. So I get to come all the way over here to 5, and I think that over here at 5 it's going to be a little bit taller. So I just need to find the y coordinate when x is 5, and so that I think is going to be 5, 3 based on this function. And so I think the absolute max is at 3. Absolute values we don't like to have to take the derivative of. It's just a little bit complicated. Okay, and then 9 says find the extrema. So again, same process. We're going to check the endpoints. Okay, we'll check those here in a second. We're going to take the derivative. So let's see, that 2/3 pops down, so it's going to be 2x to the -1/3 minus 2. And our job again is to see where this is equal to 0 and where it's undefined. Okay, we kind of have to look for both here. So I think it does help us to simplify this a little bit. That's the cube root of x. And so I can definitely see that 0 is going to be an issue, so I probably should check that one because that's a spot where our derivative is going to be undefined. And then also where this is 0, I think we'd have to have x is 1, which is also in that interval. I'm kind of guessing and checking that solution there rather than doing it algebraically, but I just need it to be 2 minus 2 to get 0. Okay, so now if I plug in a -1, again, you can check me from earlier. I got -1 for that. And then if I plug in a 3, I believe I got, well, actually I don't have that one, so we'll get out the calculator here in a second. So it would be 3 times 3 to the 2/3 minus 6. We'll figure out what that is here in a second. F of 0 is 0, and then f of 1 is going to be 3 minus 2, which is 1. So I need to get out my calculator and figure out what f of 3 is here. So let me get that out. This is where you can fast forward a little bit and wait for me to get the calculator open. Okay, so let's find the decimal for 3 times 3 to the 2/3. And then minus 6. And I better do diamond enter there. So 0.240. Okay, and I'm kind of running out of space, but we can tell here the absolute max looks like that. Absolute max. And then the absolute min must be this one. Okay, so this is the spot where I would pause. We're going to skip example 10 because you need to know a trig identity for that. So we're going to skip that. This is where I would pause and I would do numbers 1 through 22 on the assignment. And then once you feel comfortable with those problems, then come back to the video and we'll finish up on what's called the mean value theorem. Okay, we're going to skip out a little bit on, I guess we won't. I was going to skip this, but I think it's okay. What they want us to do here to just kind of see what the idea of the mean value theorem is draw a secant line through the endpoints that they have there. Okay, and I'm going to do my best. I'm not great at drawing with this tool. Let's see, what 2 points do we want on? I guess it's weird on 15 because we can't even draw a line. Okay. Okay. And then it says draw all tangent lines that are parallel. So kind of find the spot where the tangent line would be parallel. Now this one, I don't know, it's possible there's one down here. Maybe I'm not sure about that one. This one, maybe here, maybe there. This one I can't really draw anything. And then this one, I would want to draw the tangent line there, but I also know that that doesn't exist right there. Okay, so just to make sure that we're kind of talking about why he wanted us to do this, is he wants you to notice the places we could actually for sure have parallel lines, or when we had a function that was continuous, okay, so that worked, and differentiable. So this one wasn't differentiable at some point. Remember, we can't take the derivative as sharp turns. So that's why we had a difficulty trying to draw the tangent line on 13. And then 14, again, we weren't quite sure, but again, there's a discontinuity there. So that makes that an issue. Another discontinuity and another discontinuity. So he's going to kind of talk about how our mean value theorem has to have functions that are continuous and differentiable. Okay, so he kind of has those pictures here. And so this is something kind of similar. So if we draw the secant line between these two, okay, and then maybe between these two, and then these two, and then find the parallels, right? So somewhere here-ish. I'm not doing a good job of drawing that one. This one has a couple of locations, I think. This one has like maybe 3. Okay, and so what we're eventually going to find, and again, notice all of these, at least in the interval we were talking about, were continuous and then differentiable within, that we could find a value where the tangent line was parallel. So to me, it almost looks like that one happens when C is 3. And this one happens at like maybe 3 and 5, because maybe they're being nice to me. And this one happens at, I don't know, maybe 2.5 and 3.5 and 4.5, I don't know. Just a quick glance on a computer. Okay, so that's what we're going to try to find with this mean value theorem. We're going to know that there's this secant line and we're trying to find the parallel tangent lines on here. So what I want you to notice is this highlighted thing he has. I almost would write it differently. What we're going to do, because when lines are parallel, their slopes are equal. So the way we find slope in calculus is by doing a derivative. The way we found slope in algebra was to do this y2 minus y1 over x2 minus x1. So that's really this highlighted thing he has here. That's all that's doing, is setting the two slopes equal to each other. Okay? So that's what we're solving for in the mean value theorem. So on example 20 here, we're going to find the values that satisfy. So again, we're going to take the derivative here. And again, let's think of this as 3 minus 6x to the negative 1. So let's take the derivative. So f prime of x, maybe we should label that a little bit here, is going to be a positive 6. x to the negative 2. And then our old slope formula, so we're going to go y2 minus y1 over x2 minus x1. Okay, they gave us the x's. We're going to have to find the y's. So when I plug a 6 in here, I get 3 minus 1, which is 2. I plug a 3 in, I get 3 minus 2, which is 1. So I think I get 1/3 here. So now my job is to set these two things equal to each other. So I'm going to call that 6 over x squared equal to 1/3. And I'm going to do cross product there and then solve. So technically x should be plus or minus square root of 18. But remember the interval that we're talking about up here, 3 to 6. That negative root 18 is not going to fit. So the answer that we want to make sure that we circle is the positive square root of 18. Okay. And I think that's the only example he has here. I would kind of like to jump to the assignment and just answer a couple of questions. Again, after 22. This one says, does the mean value theorem apply? So what you're really looking for in these problems is whether the function is continuous on the interval. That's your first question. And then, is it differentiable on the interval? So let me see if I can find an example of where those fail. So 23, for example, I know that that's a v, and the corner for the v is at 0, which happens to be right in the middle of that interval. So 23 is going to be a does not apply, doesn't apply. And that's because it's not differentiable at 0. F is not differentiable at 0. Differentiable. Okay, and then let's find, I'm going to look at, I think 28 is the one that pops out to me. That one's not going to apply because we have something that's not continuous at 4, which is right in the middle of the interval. So doesn't apply because f is not continuous at x equals 4. Okay, so that's what you're looking for on those. Just wanted to make sure that we did one of those. Okay, go ahead and finish up the assignment now.